It's still burning daylight. And today our first speaker is Dr. Cristobal Petrovich. Cristobal is visiting us from University of Toronto. He's currently a postdoc fellow at Canadian Institute for Theoretical Astrophysics. Cristobal did his PhD at Princeton University, and he did his undergraduate at the University of Calibrating in Chile. And he's originally from the Chilean Patagonia, which is one of the southernmost settlements of the American continent. But the academic journey has been taking him to the north all the way. And he's an expert on the formation and dynamic of evolution of planets and stars. And today he's going to talk to us about the emerging black holes in spherical nuclear star clusters.
Okay, thank you, Yanya. It's a pleasure to be here. I have the chance to tell you a little bit about something that is new to me, that is galactic center. I mostly work on exoplanets. And the main question that I try to address is whether a sizable fraction of the black hole mergers that people have detected, the LIGO-Virgo collaboration have detected, do occur in nuclear star clusters in the center of galaxies. This is a work that I've done, recently published with Fabio Antonini, who is the real expert here in the galactic center part. To be in the same page, this is an image from a Spitzer 4.5 microns corrected by dust. This is the central 100 parsecs of our galaxy. If you zoom in even further, you see this overdensity right here. That's the diffuse light coming from the galactic center. And one thing to notice, this is the central 10 parsecs, is that the mass distribution, the light distribution here is not globular. It's a little bit flattened, and people have measured this to be of the order of a few tenths of percent the ellipticity of this cluster. If you zoom in even further, you see this population. This is the central parsec of stars, and with that you can measure by having near-infrared astrometry, very precise astrometry, the motion of the stars, and get the mass of the supermassive black hole at the center to be something like 4 million solar masses. This is the most recent work on trying to characterize the population of stars in the center. This is a work by Chatsopoulos, using essentially the diffuse light, the proper motions, and the line of sight velocities, and try to constrain what is the profile of the point sources of the cluster. What is the mass? This is mostly coming from, of course, the lightest stars that dominate the mass budget. And this is fitted here. This is the surface density. This is roughly 4 parsecs, a 2 power law, breaking roughly at 4 parsecs. So you can think of like the cluster being, the effective radii being somewhere several parsecs. And most of the gravity is dominated inside the central parsec. If you average, you integrate all the mass, inside roughly 1 parsec, the gravity is dominated by a supermassive black hole. You can do even better. This is, again, the profile of the axis ratios of the ellipsoids of this cluster. You have the B over A and C over A. You could see, this is the central parsec in this box, that as you approach roughly the center, where the mass is, the dynamic is dominated by the black hole, the ellipticity could be of order pretty much unity. But I will assume throughout the work that is roughly of the order of 10%. So this is the summary. We have a black hole, 4 million solar masses, following roughly this profile up to here with some ellipticity. That's going to be a free parameter. Is this representative of most galaxies? Well, to some extent, yes. If you look at early type galaxies, like M31, there is a sequence here by Georgiev and Burke. There are key features that are going to be using. And the key features are, in these galaxies, you have active star formation. Most of the young stars sit at the center of the galaxy, and they're essentially non-spherical. This is a classic example of the double nuclei from M31. You can have nuclear disk and so on and so forth. So it seems to be somewhat representative, our galactic center, in that respect. What do we know about binaries? This is one example of an spectroscopic binary. First of all, we know very, very little. There's been this work trying to account for what is the binary fraction. They essentially detected in the survey 2 out of 13. And with that, they can constrain the binary fraction to be roughly in this range with a 95% confidence. And this is one example that's going to be very useful for the rest of the talk. So this is a long period binary, almost 1 year period. So semi-mirror axis with 5 AU, very luminous, 2 million solar luminosities. And that will be essentially the progenitor of, in principle, 2 black holes. Where do these binaries, or where do these massive stars that are going to be the progenitors of the black hole sit? It's a work by Burke, showing here essentially some of the point sources. The bigger the circle, the brighter the star. So they constrain this to be roughly in this range of separations from the supermassive black hole with this power law profile. The bottom line here, most of the young stars are roughly in the central parsec, around 0.1 parsecs. They did the same for eclipsing binaries, and everything seems to be the binary fraction consistent with the binaries in OB young associations in the field, in young clusters, sorry. Why do we care about binaries in the galactic center? Well, this is a list of applications where binary dynamics might play a role. I don't have time to actually go through this, but there are many interesting applications. And the one that I will describe today is whether black holes can merge at a high rate compared to some other mechanisms in our galactic center. So this is the current catalog of waveforms from the LIGO Virgo collaboration. So essentially 4 detections plus this relatively high confidence trigger. And the question is, how do you go from here, from the main sequence, to an actual merger? In other words, this is the time scale for a merger to occur. Roughly, this is the merger time scale given by this paper. What is the, how do you remove angular momentum from the binary during the main sequence so it can shrink its orbit through gravitational wave radiation within a Hubble time? That's the main question. There are many mechanisms that have been proposed. I'll come back to that. But you can separate this in 2 categories. So it could be, in principle, by changing essentially the semi-mirror axis of the binary, by isolated binary evolution or global clusters by exchanges, essentially. Or excite eccentricity to extremely high values, and then reduce this merger time so that actually even wide binaries can, in principle, encounter each other and merge. And this is the scenario that we'll be discussing today. Why the galactic center? It's a very small part of our galaxy. There are a few advantages. This is mostly compared to other dynamical mechanisms. There is ongoing star formation. This is unlike globular clusters. Binaries are not isolated. They evolve dynamically, as I will show. They have high escape velocities because you have a supermassive black hole sitting at the center. So you have supernova kicks. It might be more resilient from actually escaping, for instance, escaping from a globular cluster. This is the bottom of the potential well of the galaxies. So massive stuff falls in, right, by dynamical friction. So you can, in principle, replenish any material binaries. There could be AGNDs that allows for extra dynamics. And of course, the disadvantages are this is a small fraction of stars live there. And binaries are generally not very long-lived. They're soft binaries because the orbital velocities are very high. So essentially, after a few encounters with other stars, they will evaporate eventually. How do binaries evolve in the galactic center? So this is the core. This is going to be the part about dynamics, which is my specialty. As I said, the young stars sit roughly at 0.1 parsecs. The gravity is dominated by supermassive black hole, so they essentially follow nearly Keplerian orbits as a first approximation. This is a complicated problem. You can think of these two Keplerian orbits, the center of mass going around the supermassive black hole, and the binary going around their center of mass. And a bunch of lighter, in principle, lighter stars going around. It's a complicated problem, very hard to resolve like with just direct embodied integrations. And there is a sequence of timescales that come into play. This is a list of timescales increasing in this direction, downwards. This is for a 10 AU binary at 0.1 parsecs. I will describe some of the timescales later, but this is just for you to have in mind. You have the dynamical timescale for the inner binary. I will call this, well, the inner binary. That is roughly 1 year. The outer binary, the center of mass going around the supermassive black hole. The timescale that it takes the binary to be torqued by the orbit of supermassive black hole, because through the lead of cosine mechanism, but I'll describe in a minute. The precession due to the cluster mass, the main sequence lifetime. There are resonant relaxation processes. There is the evaporation timescale and two-body relaxation. It's a complicated problem, and people have started looking at this. There's a list of papers here. And as a first approximation, you can, in principle, say, what if we ignore the effect of their environment, the effect of the cluster? This is the approach, and it becomes essentially a three-body problem. So you go from here to something that looks like this. And we know how the three-body problem in this very well-separated configuration operates. And it's mostly through what is called the lead of cosine potential. So you have to think about this like two Keplerian independent orbits. They interact through this potential, and the idea is that you smear out the mass of this. Now the black hole is going around the center of mass of the binary. And you ask the question, what is the effect that this potential that you create by averaging all this mass in this wire has on the inner orbit? And you can define this with some orbital elements, the angular momentum vector and the eccentricity vector. And the reason why I'm showing this is because it shows explicitly, in a very simple expression, a few key results. So this is the potential of the interaction between these two. It happens over long timescales. And the key thing here is that the potential doesn't really depend on the eccentricity of the outer. So essentially, the potential, the interaction that the inner feels is independent to rotations of the outer orbit, right? So it doesn't really depend on the eccentricity of the outer. So there is an adiabatic, there is an invariant due to this symmetry, and that's essentially that the angular momentum vector in the z direction is conserved. Or, in other words, this quantity is conserved. There is another key result that comes from this, is that this problem is actually unstable. So you have eccentricity inclination oscillations in these cycles that have a time scale given by the amplitude of the potential. So if you start with nearly orthogonal orbits, the inner binary can reach unit eccentricities formally. Therefore, you can have a merger. And the maximum eccentricity is this very well-known result that depends on essentially the initial inclination. You go from 0 to some maximum eccentricity. But this is one problem with this scenario, is that the parameter space for this to happen is very limited. For a merger to occur from a binary that is a 10AU in a few cycles, you need eccentricity to reach something like 0.99999. That means that the inclination has to be really, really nearly orthogonal within 1 degree. So that's where we come in. This is the second level of approximation. What happens if now you consider the effect from the cluster itself? There are two main effects. So this is, again, the same cartoon. But now you have this smooth potential acting on the binary, mostly changing the outer orbit. There is a spherical mass distribution that is going to make the orbit, the outer orbit, undergo apsidal precession. And it's given by this expression over here. This is the dynamical timescale times the mass of the black hole over the enclosed mass of the cluster. Very simple. And it's something like 10 to the 5 years. Now, if you assume that the distribution is flattened around some z-axis, it's actually, our galactic center is flattened on the direction of the plane of the galaxy. So with some degree of flattening, now this orbit is going, the angular momentum of this orbit will undergo nodal precession around this axis. And this happens in a longer timescale, and that longer timescale is the same as this one, but just depends on the degree of flattening. So roughly 1 million years. And this is actually a very interesting timescale, as you will see in a second. So now the dynamical problem is, how do the inner binary evolves when you have a 2 timescale problem? The inner binary changes in this Lidov cosine timescale because of 3-body interactions. The outer angular momentum changes due to the cluster. What happens? Well, the first thing you have to notice is that this is no longer conserved. That was conserved before in the 3-body problem, the angular momentum in the z direction, J in over times J out. So you allowed for mutual inclinations to vary in time, and you might expect from this that you don't need to be in this nearly orthogonal configuration for a merger to occur, and that's key. The dynamical behavior will depend on this parameter, the results that it will show, and it's essentially the ratio, of course, of these 2 timescales. But the key point here that we realize is that it does depend, is ordered unity for fiducial parameters that we assume for binaries, where the binaries are observed. So this is a relevant timescale. So these are some of the results of integrating the equations of motion, trying to see whether you expect many mergers to occur due to this mechanism. So I'm comparing 2 things, epsilon 0 and epsilon unity. Epsilon 0 is no cluster, epsilon unity, both timescales match. And this is showing the maximum eccentricity as a function of the initial inclination of the orbits. When you randomize J in and J out, this is what you get. This is the analytical expression that I showed before. And in black here, this is after 100 oscillation cycles. And you see that this is 10 to the minus 4, 1 minus c. So all of these are going to be mergers. And even if things start being pretty much aligned, you're going to still have a merger. What is the amount that you actually gain by adding this? So this is the CDF of these integrations over here. Again, merger is somewhere in here in 10 to the minus 4 to the left. So you can increase here the allowed phase space for a merger in a factor of like something like 40. So it's actually very relevant. Do you need the epsilon to be unity? This is showing the same curve, the black and the red, but now with a 10 times faster precession and 10 times slower precession. And you still get it almost always an order of magnitude increase in the way you populate these collisional configurations, orbits. This is showing for our galactic center what is the allowed phase space for this process to take place. This is the semi-mirror axis of the outer, the semi-mirror axis of the actual binary. These are different contours here. This is assuming that epsilon is 0.1. The total mass of the binary is 20. And these contours show this parameter of epsilon. There is a region that is forbidden here because if the inner orbit has a small semi-mirror axis, it will undergo precession in a very short time scale. So it quenches this process of exciting the eccentricities. So this is a forbidden region. And then you cannot undergo an indefinite number of cycles. You're limited by the fact that the binary will evaporate eventually. So these are contours here of how many cycles, either cosine cycles, you can undergo before evaporating. 100, 1,000, 10 to the 4. So in this shaded region by hand is roughly where you expect most of the mergers to occur, if any. So in the last part, I will show the result from a population synthesis model using this dynamical evolution. And we start with the IMF suited for the galactic center, the population of young stars by this previous work that I showed by Burke. And then since we don't know much about the semi-mirror axis distribution, the period distribution of the binaries, and the mass ratios, we assume that they are the same as OB stars in the field. We use a binary evolution code, assuming some supernova kick distribution from a Maxwellian. And with that, we get essentially the orbital elements for the black holes that you get. Many of those black holes are going to be essentially ejected because of the supernova kicks. Many of them undergo common envelope, and we ignore all the ones that undergo common envelope. We just stay with the ones that are pretty much unaffected. And the green dots here show the results of the ones that actually merge when we include gravitational wave radiation and post-Newtonian terms. There is a mass spectrum, so they all not fall in the same figure that I showed before for the available phase space, but most of them do. Most of them are clustered around this epsilon of around unity, so which is consistent with what we expected in the first place. If we vary the ellipticity of this cluster, going from something that is roughly globular and a little bit more flattened, unity would be essentially having a disk. You can increase the merger fraction from something like 0.1% when it's globular to something like 10%. So you gain roughly 2 orders of magnitude. And the borderline here, more elliptic cluster, lead to more mergers, which is an interesting observation. If you take one step further and ask the question, how does it compare with the LIGO rates? There are tons of uncertainties here, but I'm trying to be very transparent in what I'm assuming here. And this is more or less order of magnitude calculation. So first we start with the star formation rate inside the 3 parsecs roughly. And that is roughly essentially the mass of the cluster. If you assume that the star formation is continuous in time, you divide just by 10 gigayears, you get something like this. There are some other works that have done, of course, way better, but it's in the same order. You take again the binary evolution code, and you get a rate of binary black holes that is roughly in this range. So you create, at some steady state process, create these binary black holes. You know that 10% of them actually merge. So in our Milky Way, the rate would be something like this value, or 1 every 2 million years. Now, if you want to convert this to per unit volume, you can assume that all of these mergers occur in Milky Way galaxies, Milky Way-like galaxies that have a certain number density. And with that, you get a number that is 10 per gigaparsec cube per year, compared to the LIGO rate at 90% confidence that is roughly in this range. So in principle, it's in the low end, but it might be consistent. You might be off by, this calculation might be off by a factor of 10 either way. Most of the uncertainties are in the star formation part. But the dynamics, this 10%, is something solid and new, we think. How does it compare with some other dynamical mechanisms? There could be some of the black holes that have tighter orbits. They can mass segregate towards the center. People have recently computed this number, get something in the same units of 1 to 3. Globular clusters, through a sequence of 3-body interactions, get a number in this range. Triples in the field also get a similar number, and direct captures in galactic center get a number like this. So they all seem to be getting numbers in the same order. The hope in the future will be to actually say, well, this is the dominant mechanism. Chances are they all operate to some extent, but one has to be essentially leading, or a couple of them, not all of them. For that, this is like the story of the hot Jupiters, to some extent. We first detect these very massive black holes that are merging, like the hot Jupiters at some point we detected from radial velocity surveys 20 years ago or so. And at some point, you could disentangle different migration mechanisms by looking at the orbital elements. In particular, we learned a lot about the hot Jupiter migration scenario from spin-orbit misalignment angles. So one hope for the future, when we start getting hundreds of LIGO detections, that we can be able to measure this chi-effective parameter. These are the posterior distributions for these events in this paper. That might teach us whether they come in a sort of isolated fashion or, in principle, come from these dynamical channels. Another interesting part is the eccentricity. This is from LIGO, the three-body interactions in globular clusters. In galactic center, globular clusters are isolated. So this comes in very eccentric orbits. So when they enter the 10 Hertz channel from LIGO, they might still have some residual eccentricity that might be detectable at the order here of like 0.1. But for LISA, it might be even better to actually detect these different eccentricities, different predictions from the models. So this is missing analysis. We're working on this right now. And there is missing physics in this problem, trying to go beyond the smooth potential approximation. We haven't really modeled the fact that the stars come in and can, in principle, change the orbital elements of the binary. At some point, they come many times that they essentially ionize the binary, but the process of going through this evaporation process, we haven't really modeled, and the resonant relaxation processes we haven't either. And also some of the tighter orbits from the common envelope can mass segregate. That's something we haven't really modeled yet. So to finish, I leave you with some of the key results or messages. So dynamics of binaries in the galactic center is essentially very different from the rest of the galaxy. It's a very special place. It's highly interacting, and you have a three-body system with a massive, supermassive black hole at the center. The cluster potential plays a critical role at determining the merger rate of black holes. And we term this mechanism the cluster-enhanced lead-of-cosine mechanism, and in principle can explain a significant fraction of the LIGO sources. I'll finish here. Thank you very much.
First of all, sorry about the World Cup result. People in the room in the same boat. So does mass loss make any difference to this? And if so, how much? It wasn't clear if you included that in your...
That's included in the code itself. So we use this code from early 2002, and includes the effect from the supernova kick, mass loss, and so the orbits do expand, and that actually helps. I haven't really explained this. But you can go from here, where you are forbidden by GR, so you avoid yourself from like merging during the main sequence, because you live somewhere in here, and then at some point, GR precession, because you expanded the orbits, you lost mass, becomes a longer timescale process. So you go from here to here, and you can become active. It does actually help, but it's included in this code. that people normally in the field use.
How much should the globular cluster rate be enhanced by the presence of intermediate mass black hole?
Oh, that's an interesting question. I thought about that a little bit. Intermediate being like 10 to the 4-ish. So the dynamics would be actually similar, but globular clusters are more globular. So in principle, you could have resonant relaxation processes. So it's essentially like scaling down the dynamics we described here, with the caveat that now it's a globular cluster, so you don't have this, in principle, axis of symmetry. But the orbits, in sometimes, is very close to the black hole, to the intermediate mass black hole, can torque each other, and you can have something like resonant relaxation happening that changes the orientation of the orbit. All you need, actually, in this dynamical mechanism is to change the orbit of the center of mass of the binary. I think it would be promising. I haven't really done the math to say, yeah, sure. This is very, very new stuff for me.
So another process that must happen is the 10 solar mass black holes falling into the million solar mass black hole. And can you relate the rate of those two processes?
That's an interesting point. The short answer is no. I haven't done it. Actually, everything here happens in situ in a relatively short time scale. But as I said, so some of the tighter black holes that can live there for essentially Hubble time, they might go very close to the, or they can also excite their eccentricities and come very close to the supermassive black hole. But it's not the regime that we studied. So the short answer is I don't think I have responded to the question. We haven't really looked into that. But it's an intriguing possibility that you might trigger the two events or something like that.
Sorry, I might missed it. Early part of the talk that you may have mentioned it. Does this apply to neutron star binaries as well?
We did it as well, and the rate is very, very low, mostly because of the supernova kicks. If we assume that the supernova kicks are momentum conserving, and they are like a few hundred kilometers per second, you will probably ionize most of the, unbind most of the neutron star binaries. But the dynamics is there; it would be essentially the same. It would apply to any binaries actually. So that's another venue. It's like, does it really apply to mergers of main sequence stars that can, in principle, rejuvenate and give you this population of Bruce travelers or something like that? So the rate given this binary evolution code is very low because most of them become unbound. But in principle, it would apply in the same way.
Absolutely. It's not the same Cristobal. Our second speaker today is Dr. Douglas Burke. Dr. Burke is currently an astrophysicist at the Chandra X-ray Center, and he's originally from UK, and he did his PhD in Durham. And so many of us are GitHub users, and we always want to confirm what Chandra is actually doing now. So for this purpose, Dr. Burke actually contacted Elon Musk and to ask him to build a interplanetary rocket to monitor Chandra. But Elon is currently very busy with the development of the Tesla Model T. So for the time being, Dr. Burke wrote a website to monitor Chandra, and today he's going to talk to us more about it.
Well, A, I should say you shouldn't necessarily believe 100% of what you read in talk abstracts. And B, if I can't even get my laptop to work, it's going to be a rather short talk. It was working, as some people can attest, but I have no idea what magic buttons I have to press. turn it back off on and off again. I purposely didn't pick a live demo for this because I thought there was going to be enough trouble, but aha, you can all find out what my password is. Or if I can remember my password. Nope.
Not enough characters.
Oh, sorry?
Not enough characters in your password.
It's only 8 digits.
Change it every 90 days.
Let's see if this is working now. It's my day for technology. So this inauspicious start to a talk where I wanted to work out how we could provide some of the excitement of doing astronomy to people. I don't know if you've seen, Randall Smith has a great overview of the observation cycle where you have, some scientists sitting there hard at work, they come up with an idea, they write a proposal, they send it in to the reviewers who go and review it, who turn it down for some little spelling typo, and the cycle repeats eventually, and eventually, if you're pig-headed enough, you get time, and then there's like a cycle that says, oh yeah, it goes to the archive, they go and observe it, and it comes back, and then they have people going off. So we're looking at that little bit here with the, how does Chandra get the data? How do we schedule it? And it's sort of a more real-time thing. My science work is on galaxy clusters, so real-time for me is anything less than about 10 to the 7 gigayears. So here we have stolen from the Chandra site. Sorry, I misspoke. The way my son eats food, it sounds like 10 to 7 gigayears. I meant 10 to 7 years, sort of thing. Well, what's the odd factor of 10 to the 6 between friends? So we have Chandra is in orbit, as you see, and so it's what are we doing? It's what Chandra's doing now and what it's done in the past, and a little bit of what Chandra is doing in the future, but that's very limited. We have a bunch of Twitter handles here. Chandra itself has a Twitter account. I have one if you're really bored. And we also have one for Chow, that's who are paying for me to do all this, so please follow that. Top 10 facts about Chandra, in case there was anyone here who didn't know about Chandra. The first one has absolutely nothing to do with this talk, but it's really cool. You can get a 3D print of Chandra, and actually, like Kim Koala Kand and people are looking at how you can take some of our our 2D resolution data, something, make 3D models, and actually learn science from it. It's not just a Chandra people doing this, and a bunch of other people have done this, but there's lots of really cool stuff there. But that's, as I said, that's just a taster. I should say also. You may notice there's like 34 slides in here. That's all thanks to Paul. I said I had 20 slides, and he said, no, I needed more, so we're getting 34. And I'm going to try and get through as many of these before actually showing a picture of the website. So Chandra is one of NASA's 4 great observatories. I do feel they may have missed a naming opportunity. We've got the fantastic Hubble telescope, who none of us in Chandra are at all jealous of when they get all the press releases. We've got the Compton Gamma Ray Observatory, which was studying the invisible universe. We have Chandra studying the hot, fiery universe. And we have Spitzer, who, and this is why I'm really struggling with this analogy, I'm going to say was covering, studying hopefully rocky planets. It's about as close as I could get for Ben Grimm. As I mentioned in the abstract, Chandra is in a highly elliptical orbit. There are people in this room who can tell you much more about this. Its maximum distance from us is roughly a third of the way to the moon. And I've stolen this page from this screenshot from a page that Jean's just been working on. And we can see in the far left over there a wonderful image of Earth with Chandra drawn perhaps not to scale. and some details. These are perhaps not the friendliest of details that we might provide to the users. One of the things that apparently working on the Chandra thing is you have to work in things like day of year, so you get, instead of sensible dates, I mean, we all have our bugbears with dates, but you know, these are really quite annoying to work with. Year, day of year, hour.
We do have that really annoying time signature right next to it, though, for people who can't think. Proper.
I'm not sure I would quite put it as people who can't think. And I don't know, it's a shame this didn't come out. So one of the things about being one of the reasons for showing that previous thing was to remind me to talk about the fact that Chandra isn't actually, we're not actually in constant contact with Chandra, unlike, say, XMM. And this actually has impacts on the website because we have people who come together to make these loads. They get uploaded to Chandra. I think there's like normally a pass every 8 hours, is it? So there's normally 3 a day. And you can then go to the Deep Space Network Now website. If you've never been, it's really cool. You can see our telescopes, our ground-based stations trying to shoot down our telescopes with electrical waves. I don't know why at this time this was meant to be during a pass, but apparently Chandra wasn't contacting them. There's whatever was going on there. So that's a neat little website. And also there's an archive, and this is actually where I get essentially all my data from for doing this. This has sort of been a skunkworks project, so I was using stuff that was publicly accessible. I wasn't really sort of using sort of behind the scenes data to get at this. And this is, I don't know if you can see this, this is of one of Grant's observations of ABAL 2597, and I use this to flesh out the data. So why did I start on this project? So I was just waiting for anyone to get the really bad pun, because this was one I was actually quite impressed with. Yeah, I've long wanted to, and also trying to get ones which are CC, that I can do this without getting done by the copyright police is important as well. And I also needed to put the name on because I wouldn't have recognised who this band were now anyway. So I've been looking at this sort of idea of how do we say what Chandra is doing for a while now. And in 2008, I took this website, which no longer exists, which would show where Chandra is. So you can see there's a latitude, a longitude, and an altitude. And this was, you know, simpler days when we were actually, new information on gamma ray bursts was still a hot topic. And Kepler hadn't even been launched yet, I don't think. And so I would take this page, which is now no longer exists, and work out where it was over Earth and just put out onto Twitter. I actually started the Chandra X-Rays website, the Chandra Twitter feed. It's now a lot more informative than this, but it doesn't have quite as many updates because, you know, that page was updating 1 a minute, and, you know, Chandra's moving quite fast, so you get interesting information on where it's going over quite a lot, although it generally was, as I've made the joke before, it's generally in Russia. And so you would get some responses from the public at this. I didn't really respond to them. And this was one of my favourite ones. And people on my corridor probably wish I was. And this, those previous slides were from a presentation I gave to a semantic astronomy workshop in 2009. And one of the notes I'd left in that presentation was saying, you know, what I really want is something that says Chandra's about to observe your favourite object, well, my favourite object for the rest of the time, because I don't care about your science, I want my science done. And, you know, that was 2008, 2009. Everything has changed now. We now have actually Twitter feeds which are a bit more informative. We have on the left one showing what the HST is observing. Normally you would get a nice little cutout on the Sloan image, presumably that if that had been covered, but this one, when I grabbed it, happened to be of a solar system object, and this one is one actually of Grant's cluster. It's talking about Grant's observation, the one that I showed you from the archive. So this is where I actually start talking about the website, and this is what I'm doing from. I start from this. This is the Chandra short-term schedule, full of lots of interesting, dates as we talked about, and various other names. Name of the field, how long it is, what instrument, grating, position, and some other things. So how do I make profit out of this? Well, actually, I should back up first. This is a view of reality. You can get a bit more detailed. This is back from Gene's page, which is actually augmenting this with more information on the comms pass, and I don't include that information. I think it would be interesting perhaps to have something to say, hey, look, Chandra's actually being talked to at the moment. But you can actually go even more detailed than this. You can get information on, if you really wanted to, about, say, the gratings moving in and out, and I think that's likely to be a bit too fine-grained for the sort of aim I'm going for a website. And this is actually, I got halfway through the talk, and this is the website itself. I don't know if many of you actually have managed to look at this yet. And so this is talking about, this was taken the weekend, and it's talking about Grant's observation. I have the Twitter feed on the side as well, and there's some synergy between the two, so that at this particular time they're both talking about the same thing. And we've got the current observation, a little bit of text about it, and some information. These are images I've taken from, essentially, that was available from that short-term schedule. This particular shows the optical field of view with the approximate chip placements. If all the chips were on, you can switch, as I'll show a bit. There's like X-ray from the Rosat All-Sky survey, so generally you've got data for all parts of the sky, but it's not great in depth or resolution from the pointed phase of the Rosat.
Why don't you have the scale?
You mean on here?
On there.
On this? Because this is nothing to do with me. I'm just stealing this. Thing.
What is it you put there, everybody?
This is just the Twitter feed from Chandra, Chandra's Twitter feeds. So.
But the image itself, is that the data that were just taken, or is that some?
You would have to speak to Kelly or whoever did that.
Just a press release
Yeah.
observation. It's like the top result when you Google the cluster.
Yeah.
So, if you're showing the current observations, though, yet you're using an image from a previous observation of the same source?
Well, first of all, I'd like to reiterate, this is, I have no control over what goes in here. This is just a
Well, you have to control whether to show it.
I have the control whether to show it or not, but, I don't know what's going to go in there. I could take it out, but I felt it was a useful thing to put in. And this is one of the reasons that I have for this meeting, is to work out what people find useful or not.
This is for the public.
Yeah,
so
but
the
this.
public can say, hey, Chandra's looking at this exciting new source.
Yeah.
Yeah, but
Yeah.
if we put an image up there, if the only image we have is like the thumbnail of the new image, those are proprietary data, so we
Yeah,
can't
exactly.
put them on a website.
No.
Exactly. So this is a picture
Yeah.
that we happen to have. Not dig up out of public view.
But some targets we look at, we don't have an image.
Yeah, and
Yeah.
there's
So
not
what we
always.
have, right, then?
Well, no, there's nothing. There would just be some other piece of information that they have in here, and this is, there's because of this. You actually this makes it look like this is there's only one post. There are more posts than this, but you just can't see them on here. And actually, there is an interesting viewpoint because I have. When I started this, for various technical reasons, and because I didn't want to pay for it out of my own thing, I had a limited number in this. Now I've actually managed to convince Jonathan to let Chandra pay for this, so thank you, Belinda. I've sort of tried to backfill to essentially the start of the mission modulo some crappy data I've been able to recover. And so for observations which are now public, I technically can, on this page, include a Chandra image. Unfortunately, as I mentioned before with HST has these wonderful images. A lot of Chandra images aren't particularly spectacular for the public, so it's an interesting question of whether we should show that. And also, I've taken that down at the moment because I was annoying the archive because I was using an interface that I shouldn't have been using.
Remember when you asked a simple question about a scale and you triggered a whole discussion?
I know who the problem people in this audience are now.
Well, maybe you could just have an explanation of where the picture comes from above it. This, and here's a picture of this which we Googled from the archive.
Well, I mean, Twitter now has 280 characters if you are one of the anointed ones, and I'm not sure whether Chandra is sort of thing. But presumably, if you follow that link, you would get more information on where that image is from. On this thing, for my images, if you go to the views thing at the top, you can actually find some information on that, on what these things are. So talk about this, talk about large images. As I said, there was various images. We can look at the PSPC, the ROSAT images to show the X-rays. There's a details tab, which is for the Astro Nerd, which is basically just a table with the values in. So that it's essentially a straightforward copy of the short-term schedule sort of thing. And then the interactive one at the moment uses the Worldwide Telescope, and it looks more impressive than this screen because when you go there, as long as you're using the HTTP version, not the HTTPS, then it will actually animate and scroll around and zoom in, and you can scroll around a bit. And there's, for those who care, I'm wondering about playing with the Aladdin Light image, because the Aladdin Light widget for showing data, because that would provide different capabilities. So the data augmentation, I'd mentioned that I take it from the short-term schedule. Well, it's a little bit more complicated than that, because I take the data from the short-term schedule, then go and query the archive to go and find out more information on the actual observations. But then in these presentation stuff, I'll explain what this half-eaten grapefruit is in a minute. But there's data there that I take from Olaf Frohn and Jose Vieira's Milky Way outlines. This is looking at the proposal for this, so it's like a proposal view, which is Grant's proposal, it's showing his abstract and all the observations I know about that proposal. We have, for each target, I try to identify from SIMBAD, based on the target name field that the user has given, what type it is. You have the instrument, whether it was a joint observation with one of the other satellites. There's various other columns, the constellation, which I take from one of Jonathan's programs. I'm interested in looking at ADS literature type stuff and the Universal Astronomy Thesaurus for ways of mining the abstract and linking it to science, because I think it's interesting to sort of say, here's the sort of science. I personally think it might be interesting to say, here's the sort of science that people doing X-ray observations of galaxy clusters are into, but it's tricky. One of the things I have not included purposefully at the moment is the PI name on this, because there's just the worry about dealing with personally identifiable identification. I don't think that's true here, but I always worry about this sort of thing. And two, I actually don't want to make this about people, it's about the science, and because the recent discussions about Nobel and stuff, prizes, it's not individuals, it's groups that do stuff. So we don't have just science observations, there's engineering observations, sort of calibration, so there's something that gets put in there. If there is a calibration, it's a lot less interesting because I only have a little bit of text. And then this does lead to odd confusion on here, because Twitter claims that we're looking at something and I'm saying, well, we're actually doing calibration. And also, for people who are giving talks where they're screenshotting their browsers, please be careful of the other tabs that you have available, because you might find out your Taylor Swift obsession. And that you can't even spell Taylor Swift if you're obsessed with her. So this is, again, probably one that doesn't come out very well. This is one of the first visualizations I did with the data. It's a 3-day schedule, and it just basically shows on a picture of the sky. There's meant to be the galactic plane, and the colours indicate whether it's an observation that's to come or has happened, and the size is an indication of how long the observation is. You also have this in tabular form for those that are stuck looking at screens which don't have nice representations, or this. And this is similar to this is essentially the same table that you saw with that proposal abstract from Grant's. And you can see at the top when I took this, Grant's observation was now sort of well in the past. Oh no, he's got several of them. But you can actually, the blue links gives you ways to slice and dice this, so you can sort of look at, like in this particular case, I'm looking at all joint observations with New Star, and you can't really tell, but I can, that most of them are actually on the plane, which is perhaps not too surprising given New Star's capabilities and what you'd use Chandra for. But there's lots of other things you can do. You can look at them like for the ACES instrument, all ACES, and that basically everything, all ACES-I, everything. If you start looking at HRCS, gratings, then you start see again, it looks more like on the plane and stuff. But I felt it was an interesting way of just looking at the things. These are pre-canned visualizations. They're ones that I've chosen how you slice the data. And so, for instance, this one is, just looking at the category of observations that I've identified as clusters of galaxies. And, you've got serendipitous discovery. There's not many galaxy cluster observations done through the plane. So, we're doing real important science here. As I mentioned, those were pre-canned. I'm also a lot of fan of sort of faceted browsing of data, which allows you to filter and view stuff. And these, I've had previous explorations of looking at the Chandra data using this particular widget. And so it's showing like a timeline view where you've got all these little dots of the different instrument types, and you can filter them using the things on the left. There's a bunch more that you can choose on to sort of have a look at and drill down by clicking on one to get data. And then if you click on this, you would get to a view like I'd shown previously, showing all the observations with ACES. Unfortunately, there's no spatial map on this, which is one of the reasons why I have all those pre-canned observations to sort of take some of the more common ones. Here are the more, I don't want to say esoteric visualizations of the data, but ones I've been playing with. I've been taking an approach of just throwing everything at the wall and seeing which stick. So this is showing, the color shows the number of observations that start in a day. It's just too much effort to work out ones that fall over the day-night boundary. And so you've got a GitHub streak type map, and this goes all the way down to 99. It just looks things. So we have this one, which is the cumulative distribution of the observation length per cycle. And it used to make much more sense when there was only a few cycles in. Now I've got lots of them. It's actually beginning to get too much data, and you sort of go, well, how best to show this? One of the reasons that you might expect this to be the same from cycle to cycle, but as time goes on and our understanding of the instrument and our science that we're trying to go on might mean you'd push to longer observations. Then but then there's also things like the fact that Chandra's thermal profile is being maintained much more carefully now, and so we're pushing to lots of shorter observations. So it's sort of interesting to me. And then we've got a few like these ones are new cycle, and the cycle 0. So there's very few observations in these, and they're special. And there's a bunch of other visualizations that related to that. The ones that are a bit more, even more esoteric. This is taking those observations which are that I've identified in SIMBAD and basing them on their hierarchy of their object things. So you've got sort of the number of T-tau star candidates, and this goes on for several pages on this scale sort of thing. We have object of unknown nature, which is always a fun one. And it goes, as I said, several pages to show you can click on these to take you to other views and highlight and hide some of these nodes to try and get at some of these overlap things, because this is all done automated algorithm to place them. And this is the one I'm sort of going to finish on. This is interesting to me. It's what they call a Sankey diagram, which lets you show flow of data. So on the left, this has the proposal categories. We have 9. Is it 9 proposal categories? 10, like clusters of galaxies, AGN, and things. And then on the right is the observations that are from those proposals accepted in those categories, and what their target name was identified as. So obviously clusters of galaxies mainly going to go to clusters of galaxies, but there are, to BCGs, and some, they maybe look, their target name maybe of a safer galaxy or something, and sort of interesting just to see how it goes through. But most of them is actually unidentified, and that's a lot to do with the fact that our target name field that we get users to fill in has no semantics. It's just something for them to use, and so they'll use things like field 1 or biggest cluster or something like that, or even they use RxTE 1473 plus 2, and it's just not a complete one that I can identify. Now there is more logic that you could think about doing to try and track down this, but I don't know how much interest that or use it is. There's also the fact that the target field is Chandra is not a single point source instrument, it's a field of view, and you're looking at a number of objects, so does a field name actually mean that in all cases? And there's just a whole bunch of these, and you're partly seeing here is that this is based on, as I said, the SIMBAD breakdown of object types, and so where we had cluster of galaxy, is a single object. When we get down to stars, they each have their own private name because they're each star is precious to the people at SIMBAD. And that's just, as I said, just carrying on. And this is the last slide. It's just showing a year in the life of Chandra for the 4 instruments, the 4 cameras, you might want to say, just showing the number of hours per day that it was running. And because, again, I'm just too lazy to work out how it goes over flow, it's the number of hours on that day, so which is why a day can appear to be about 40 or 50 hours long. And so, yeah, one thing I didn't really say was the target of this website. I think it's interesting for scientists, X-ray astronomers. I think it could be interesting to the public. At the moment, it's some Frankenstein mishmash, and working out the best way forward is, any input would be greatly received. Thank you very much. It's related to a graph. Which one was this? This was the... It's related to sort of a tree structure, and actually people like Alyssa use dendrograms for their clustering of stellar clouds and stuff. When you're trying to find groups and clumps, you're building up sort of groups, and you're trying to provide some level of structure to say that this clump here is actually part of a bigger clump, which is itself part of a bigger clump. And so it's just a visualization. Here, really, it's just that you've got a level of hierarchies going on this particular way. I've gone from left to right, going from very broad-grained, coarse hierarchies to very fine hierarchies. And so you've just got a tree describing that structure. And so a dendrogram is really just that. It also just makes me sound cool and like I know some computer science terms. Over now.
So I'm looking at your disclaimer, and it says that should not be relied on for scientific use.
Yeah.
Why not?
Because, and I'm going to blame other people here. Like if you look at the short-term schedule, I'm keying this off the short-term schedule, and that is not 100% reliable. Like there are missing times, particularly near the start of the mission, when people may have had better things to do than fill in a website. And also just the nature of the beast. One thing I didn't really talk about was, when you have a solar flare or a replan events and stuff, it really messes my life up doing this, so can you please stop doing that? Just keeping track of that information and stuff. So, as I said, I've sort of been doing this as an outside user, so I'm just using the easily accessible stuff, so I don't, I'm not getting necessarily all the data I could perhaps be getting for trying to make sure this is as accurate as possible. Because that picture I said where, Grant's object cluster was being observed, I have no idea whether that's actually true. We only know that's true once we've got the data down, once we've had a pass, sort of thing. So there's, once it's been observed, you know, but anything there is somewhat dodgy.
Speaking of historical data, would there be some value in having a separate tracking point that is the most recent public data? It seems like the public data is interesting. That's now available. You could even go and get it from the
Yeah,
archive.
you can actually get it from the timeline view, assuming that for some level of my version of the database, that's keeping that sort of thing tracking. But it's not. One thing about the public data is you can't just say everything before April 2016 is public. It's not. It's not that easy.
The archive, what is actually public.
Yeah.
Any other questions?
But one cool thing I find about this is engaging the public for the vested citizen scientists.
Yeah.
So you have the historical, all this branching in there. But when you link it to what the current thread of science, like why the hell are you looking at the crab nebula?
Yeah.
Why are you doing it 50 times? There are those stories that are being relayed with this information. So beyond this room, the general public, why are you continuing? And just one of the takeaways is that you look at this with Chandra for 18 hours. That's not necessarily known in the general public. That's what Chandra does. It stares at something a long time because there's not a lot of photons.
Yeah.
And so then linking that to what the current thread in the industry or in the science, or why we're going back to do this, or why we want more interest. Those are interesting stories that I see this as potential to do.
Yeah, I mean, I think.
And don't downplay the PI thing. Human stories are a big thing.
It is human stories a big thing,
I
but
don't want to go there with my
but as I've not managed to get a PI proposal through Chandra, I feel strongly that we're not going to do this. No, I mean, I think this is one of the things, into the sort of the why, and how much we can automate that versus, at some level, maybe it's just a case of you have to get someone in the public ed. They already, I believe Kelly and team do actually use, the image that we had on the Chandra Twitter feed of, what it's using is based off, I believe, this website. They could do it themselves, but they found it easy to do this. And I think maybe there is a case there to have, human intervention to try and provide that information. What the best format and best dissemination of that, I don't know. Whether it's on a site like this or something. There is some automated type stuff that you could do. I know that Alberto and the ADS team are looking at various ways of mining the data, the literature and stuff. And I've worked on data literature connections and stuff before. And so I think there's things you could do automated, but I think to make it interesting to the public, I think there's definitely some human editorial need. But I do think that is interesting. Not just I do have the abstract here to say why you're looking at these objects, but it's not always what the public are going to be interested in. And also this information is somewhat hidden to get to this from the front page, but then you overload the front page with flashing lights saying, no, look at me, now this is why I'm important, so what the best balance is. Thanks.